So I'm Amos. I'm one of the co-founders and the head of the software team at eero. And who here over the upcoming Thanksgiving holidays is going to have to run tech support for family or friends? Show of hands. Okay, few people. And how about on their Wi-Fi, fixing their Wi-Fi for them? A couple. It's something that I've had to do myself many times. And at eero, we're trying to fix home Wi-Fi, so make it easier for people to use so this isn't an issue. And today, what I'm excited to talk about is how we've leveraged Scala and Akka as part of our build system, or part of our overall system, to help with this goal. And I'm excited to kind of share how you might be able to use this for your cloud-connected IoT devices if you're building something similar, or for your web services. So what are the practical examples of how we've done this? And another reason I'm excited is because I think these technologies are really, really cool. It's why we're all here today. So to give a background on what our product does is the current one router model that people use and are used to covers really well one room within the house. It covers your living room and maybe the room next to it. And this is becoming more of an issue as there's a proliferation of Internet of Things devices that might be around the house or at the very edges of the house, as well as people are streaming more video, and they're streaming it not just in their living room, but everywhere in their house. So you want fast internet everywhere. So with that, we work to solve that with having multiple devices that mesh wirelessly together and provide internet everywhere. And so to make it so the setup for these is not even worse than setting up an existing traditional router, we needed to have a cloud to really support and make it simpler to use. And so using a cloud to back this system. So our system is made up of 3 different components. There's the hardware and software running on the hardware and then the software running on it, on the eeros that you would set up in your home and that mesh together. There's the mobile application that people use to set up their networks. They use it to do advanced network configuration. They use it to monitor and debug their networks, and also to use newer features that we've been able to enable because we have a cloud, such as parental controls. And there's more that we're always working on. The devices independently talk out to the cloud. They are constantly talking to it. It's providing them with their configuration. And so the cloud component is the most relevant to what I'm talking about today. And that, in part, is because when I suggested using Scala on the embedded devices, my co-founder that was working on them flat out ignored me, probably wisely. And so the cloud is what the devices talk to and send up their statuses, their temperature sensor data, their speed test results. And then it in turn sends them decisions that it's made. It sends down, run a speed test, download a firmware. And these are all things that we've been able to do. So why use the cloud? In something that's traditionally not had a cloud component, why did we choose to go this way? Well, the first 2 up there, configuration and firmware updates, are something that we knew we wanted, and we knew we wanted the cloud to manage. Especially as if you have a distributed system of devices within the home, the cloud is actually a really nice thing to be able to coordinate that and to be able to elect a gateway and own the configuration rather than one of those devices having to have it. It's a way to offload decision making. So if anyone is working on something that has maybe less compute power or doesn't have the full context of what's going on, any of our individual devices doesn't have much knowledge about the network as a whole, the cloud can make decisions for it. So decisions taking more than half a second, well, those should go to the cloud, and the cloud can decide, and it has the context of that network and all of our networks. So hopefully we can eventually leverage machine learning across all of our networks to make everyone's network better. And when deciding, knowing that we needed to build a cloud, and knowing that I was going to be the first one building this, as there were 3 of us up front and building out the team, we had to decide what tools would we be using. And to decide on the tool, and specifically the language we knew we'd be building in AWS, there's a set of constraints that I had to work against. And these constraints led to requirements that the language needed to fulfill. And so the first constraint is scalability. These devices, and if you have automated kind of computers that are talking to you constantly, they're much different than users in that they're always on and always internet connected by default and by design, or by definition even. So we would have a huge number of requests, and we wanted to be able to handle a large number of concurrent requests. For each eero that we have makes at least one request per every 10 seconds. So every 10,000 euros you have 1,000 requests per second, and on day one we shipped over 20,000. So we knew that we had to handle 2,000 requests per second day one, and we've grown since then. We launched 9 months ago, so think of where we might be. We also knew that we had to be highly available. So while your network is going to run without our cloud, you're not going to be able to set it up, you're not going to be able to make changes. And that was a conscious decision we made because it would enable us to do a lot more, but it was also something that we had to make sure that we handled. So Scala works really well for these requirements. It's highly performant, it's super fast on the JVM, it's compiled, runs really fast. It has easy to use threading models and ways to reason about what you're doing. And so that's worked really well for the development team. And it's type safe and has good error handling primitives, as all of you know. But this is really nice when you have a lot of information coming in from these devices, metadata, speed test results, diagnostic logs, that you know at the very edge, as you're receiving it, that it's going to be well formed all the way into your database. I love Scala. I really enjoyed working on it on projects prior to starting this company, and knew that I would be writing a lot of it, and so that did go into the decision-making process. And when we first started writing it, we didn't know that we'd be using Akka. We had kind of the thoughts that we might. Akka is now something that would prevent us from moving away from the language. It's really enabled a lot of our technologies and a lot of the things that we do. And so that's what I want to talk more on, is how are we leveraging this to do things that I think are potentially different from how we would have thought about doing them 5 years ago or 10 years ago. So why Akka? I listened to parts of the 2 previous talks, so this is a recurring theme, I believe. If people have been in the last 2, they know. But for Akka, we're using it to solve not the scalability or this availability piece, but these actually very specific problems that are hard to solve or difficult to solve in other ways. So the first is that we need to coordinate firmware updates across all of the eros on a network. So a typical network, we sell 3 packs, so it's going to be 3 devices. In SF, it might be 2 devices, due to the homes being a little smaller here. And it could be up to 10. And so coordinating those, getting them from an unknown state into a known good state on the same version. This is the coordination and the process management is something that Akka provides really well, and I'll get into how in a minute. We also want to track the status of all of the eros. Are they online? Are they internet connected? And to do that, we use heartbeats that are coming into the cloud once every 10 seconds. So we can notify the user in the application, for example, hey, your device is online, or no, your internet is down, and do that quickly. And we want to be able to track the status of them all without spending a huge amount of money to scale, or without having it take down our cloud. So we want it to be fast. And then we want to detect when an eero or a network loses connectivity. And so this is the detection of an absence of something, which is a problem that is hopefully something that people here have faced before, and this is kind of our way of dealing with that. We don't want to do a scan of the table to find a full table scan to see, oh, these are the older ones that haven't been updated recently. We want to have something that can find something is missing. So how do we do that? What is Akka? I know the 2 previous talks talked on it. I am guessing a lot of people know about actors and Akka, but I'm happy to do a quick run. Does anyone here not know what actors are Akka? Don't be shy, raise your hand. Okay. I'll do a brief intro to them. So, and Akka is a tool in Scala, or a toolkit, and it provides actors similar to Erlang. And so actors are a concurrent computational model that is based on message passing. So you have an individual actor. In our case, every eero that we have, so every device out in the wild, has its own in-memory representation in the JVM, and it's its actor, and it's a single-threaded model, and it has the state of the device. And so and it's also, because it's a message processing system, it's also a queuing system. So you have the messages come in, it handles them one at a time, which handles the synchronization because it's single-threaded, and it also it can have this state that's being updated along the way. You can actually also do it in a functional way, which we do, but you can also use vars or mutable state. So how would a heartbeat for us, which are these ways of us knowing the device telling us, hey, we're OK. It's hard to reach out to a device because they might be natted. How does that look? So you have a hop through your network. Every eero, as I mentioned, is talking individually out to AWS. I had a cloud outline here, did not show up on the screen. So you hit HA proxy, which is our load balancer. It directs it then, OK, it's a heartbeat. I'm going to send you to, this is more of a hypothetical how you might do it with if you weren't using actors. Sends it into the controllers. They talk and write the heartbeat to the database, maybe read the database to look for information, then goes back out. What our model ends up looking like is the same number of hops, approximately, but without that database call. You're not going to have to go to the database every time you're coming in. It does add additional services, which potentially makes your system slightly more complex, but it's really made our developer lives much easier. They really appreciate having this model for how they can think about these devices and the state of the devices and how to manipulate them. So digging in, actually, let's go back. So now we're here. We have our actor clusters digging in and going in, and let's say we zoom in there. So what does a heartbeat look like? So it's coming off the device. It's hitting in our system. So it's hitting HA proxy. It's being directed to one of 5 nodes in our actor cluster. These are actually across two availability zones, and they're fairly underutilized. So we could probably get away with fewer, but we're adding in the redundancy so we don't go down. So you hit your actor cluster node, each of which for us has 5 shards for 50 total shards across the 5. But you hit one actor cluster API. From the API, that's where you take this message and this request, you package it up into a message that you're going to then be sending to the actor and figure out where the actor that you want is. And so you're using the ID of the device to then go down to the actor, and then the actor might write to the database, it might not. We're actually totally fine with there being this extra hop potentially between machines part of the time, because it's much faster to do a network request even across availability zones than having to go to the database for every request. And here is really bad pseudocode, but hopefully to give people an idea of what does the actor look like for us? How are we using this to understand the state to do the detection of absence? And so we start, our actual actors are going to have a lot more state, but the relevant state here is that you have the last heartbeat and you know when you last wrote to the database. You have the receive function, which is defined for Akka, and it's where you send your message, and then it has pattern matching to figure out what is the type of message. So here we have 2 different types of messages we can have. We can have either a heartbeat, or we can have a check alive. And in this case, the eero sends it sends in a heartbeat. It's ending up in this actor. So the first thing that the heartbeat does is it updates the last heartbeat time, and it checks if it's written in the last 30 minutes. And 30 minutes here is somewhat arbitrary, but it's much better than writing it every 10 seconds. And so if it isn't there, then it writes it to the database, it updates the last write time, and it goes on. This has saved us well. So there's 180 fewer writes to the database because we're writing when things change. If an eero comes online, which isn't shown here, and it's been offline, that'll get written as well. So it's writing the status, it's alive, and here's the heartbeat. We also, as part of this, when you want to know if a device is on and when its last heartbeat was, because that's not in the database, because it's not in memcache or this other layer, and a user's using the app, it'll actually reach into the actor, because the actors aren't going to have anything blocking, and grab out the heartbeat there. So this next piece, this cancel scheduled and schedule. Here, we're canceling a job that has been scheduled and would otherwise be coming back in. because we know that we had a heartbeat. We don't need to wait. And then we're restarting the scheduled check alive, and it's a 45-second loop. So after 45 seconds, if you haven't had it recanceled, it's going to come in and it's going to hit this last case called check alive, do a double check to make sure there hasn't been a heartbeat, and then it's going to write that heartbeat to the database and potentially send a push notification to a user, or otherwise inform our users or us that this device has come offline. So this is, even having the scheduler running for every single actor we have and having it get canceled and restarted all the time is actually very performant. We haven't had any issues with this, and it's been a great way to solve this somewhat interesting problem. The next piece that I mentioned, and also through these hops to the database, because it's writing to it much less frequently, when we first launched, we were writing everyone to the database, and that was killing us. And so being able to remove these has really both saved us money and heartache and potential downtime, but also just made our lives easier. So for updates, the other part, so how do you coordinate from an actor? So in this case, we have two different actors, and the fact that actors can talk to each other well and coordinate amongst each other is key here. So we have our network actor, and then we have our eero actors. And so the network actor would know which devices belong to it and which ones it needs to update. And then you have the eeros out to the side. So the network actor might get an update or an upgrade action, which has the firmware version it needs to go to. And then it's going to send download actions to each eero actor, which then have a reference back to it. So they can always say, OK, I've succeeded. They send them down to the eeros. The eeros might succeed one at a time. It's not necessarily all going to happen at the same time. Downloads can also take up to 45 minutes on slow networks. So you're wanting something that is going to be long-lived and not take up memory when it's not in use. And then we fail, which sucks. But it actually happens moderately frequently. Maybe it's corrupted. Maybe something happened when it was downloading it. So the network actor doesn't want to have the network reboot to apply this update. It wants to retry. And so it maintains the state. It knows that these other ones are ready to go. It updates the actor, and then it succeeds. So from that success, then we're able to say reboot and get the reboots coordinated down to all of the devices. An automatic update might happen in the middle of the night and take your network down for 30 seconds as it's rebooting, and you want those all to happen at the same time. You don't want to be rebooting at different times. So from this, the key kind of learnings that we had as we were building the system, which are some cautionary tales, is that you want to make sure that if you're using an actor cluster, that you're always maintaining, well, depending on how you deploy, but that you're always maintaining backwards and forwards compatibility with your actors and potentially your persistence and how they're talking to one another. And so for us, we're deploying, because we don't want downtime, we're taking down an actor one at a time, or an Akka cluster node one at a time. It'll be running two different versions. You need this backwards and forwards compatibility. If you take them all down, if you have to, you can take them all down, bring them back up, and break that. You want to avoid blocking I/O in an actor's execution context. My pseudocode did not follow that because I was writing to the database there, but there's ways around that. So you can put the database call in a future that you don't actually care about the result of, which we do. We don't wait for the result there. You don't want to allow connected clients or devices to synchronize. If you think of a request taking maybe even 500 milliseconds, so half a second, and in a 10-second period, which is our heartbeats intervals, there's 20 of those. If your devices end up synchronizing and all of them are hitting at one of those 500 millisecond periods, you're in trouble. You have a much higher load than you should if you have it spread. So that actually did happen. We tried to avoid it, and it still happened. Don't allow, and measure everything. You don't know where the bottlenecks are going to be. I thought up front that maybe Play was going to add an overhead, and it adds none. So how do you make sure that you don't have overheads? And so the takeaways from this is that hopefully these are things that you can apply to, if you are doing IoT devices that are connected to cloud, maybe very relevant, otherwise hopefully still relevant to your web services. So this might be, how do you do absent detection? How do you find that something doesn't exist, as we do with our heartbeats and our statuses? How do you do process coordination and make that work really well for you and have actors talking to each other? And maybe it can be different types of actors. And how do you make sure that you're really performant? Our 75th percentile time for these heartbeat requests to our cloud right now is 4 milliseconds. And that is with multiple hops across different availability zones in EC2. So I think that hopefully you can apply some of these concepts to your work. I've enjoyed sharing them and have really enjoyed building this out. And I think we've defined a bit of a paradigm of how you can do cloud-connected IoT devices. And, well, so thank you.